Welcome to the Deep Dive. Today, we're digging into something pretty significant in the cloud world, Google's big play in AI infrastructure.
Yeah, it's definitely made some waves. We're talking Ironwood and Axion.
Right, their two-chip announcement. And it feels like more than just an upgrade, doesn't it? It seems like a real offensive to shake things up.
That's a good way to put it. They're definitely trying to challenge the status quo.
Okay, so let's unpack the core idea here. They're talking about moving from the age of training to the age of inference. What does that actually mean?
Well, the age of training, as they put it, was about these huge kind of episodic compute bursts needed to build a model. Massive power, but for a limited time.
Right, like training GPT-4 or something.
Yeah.
Takes enormous resources, but then it's done.
Exactly. The age of inference is what comes next. It's when those models are actually running day in, day out, serving users. Think about, millions of searches, translation requests, recommendations.
Okay, so it's continuous, user-driven, and it scales like crazy.
Precisely. And that's where the compute demand really explodes, but in a different way. It needs efficiency and constant availability.
Which brings us to Ironwood, their new TPU. They're explicitly calling it their first designed specifically for inference. That sounds pretty targeted.
Oh, absolutely. And they're not just thinking about today's chatbots.
No. What are they aiming for then?
The really ambitious part is they seem to be building for these complex, multi-step tasks, agentic workflows, they call them, stuff that barely exists yet.
Agentic workflows, like an AI assistant managing multiple things for you.
Kind of, yeah. Think bigger, though. AI that orchestrates complex processes. Google's basically building the infrastructure, the runway for the next 5, maybe 10 years of AI.
So the mission here is twofold, it sounds like. First, vertically integrate their whole AI stack, control everything. And second, take on Nvidia. Challenge that market dominance, maybe bring prices down.
Yeah, that's the competitive angle, for sure. You can't ignore the Nvidia factor.
Okay, so let's talk about the hardware itself. This isn't just one chip, you said.
Right. You absolutely have to look at it as a system. They announced two things together, basically inseparable twins.
Twins.
Yeah. You've got Ironwood, which is the new TPU v7. That's the custom AI muscle. And then there's Axion, their custom ARM-based CPU for more general tasks. They work hand in glove.
And together they make up, what do they call it, the AI hypercomputer.
That's the term, yes. It's the whole package, the complete system architecture. And we're talking massive scale here. A single deployment integrates, get this, 9,216 Ironwood TPUs.
9,000. Okay, that's a lot.
It is. And that system, that whole hypercomputer, is what they want customers to actually rent. The idea is to simplify running these enormous AI models.
Let's zoom in on Ironwood then, because this feels like a change in strategy for Google's TPUs. Didn't they used to rely more on just scale? Lots of chips working together?
Historically, yes. Scale was their big advantage. But Ironwood seems different. They're now competing directly on, the specs of a single chip, head-to-head performance.
They're aiming for parity, basically.
Seems like it. And a key piece of that is this new native support for FP8.
FP8. 8-bit floating point. Why is that such a big deal?
Well, older TPUs could do low-precision math, but they had to emulate it. It wasn't baked into the silicon.
Okay.
Adding native FP8 support is a huge nod to how modern large language models actually work. They run much, much faster using lower precision math, often without losing much accuracy.
So native support means faster performance.
A lot faster for those kinds of operations. They're claiming a 4x boost per cycle just from this, which translates to 4,614 TFLOPs of peak compute per chip. That's a massive number.
Wow. And how does that compute power get used?
It runs through their main arithmetic units. There's the MXU, the matrix multiply unit for the core AI math, and the VPU, the vector processing unit, for other stuff. Standard TPU stuff, but scaled up.
Okay, 4,600 teraflops. That needs a ton of memory bandwidth to keep it fed, right? How does the memory look?
Yeah, memory is critical. Ironwood has 192 gigabytes of HBM3E. That's the latest high bandwidth memory.
192 gigs. How does that compare?
It's right up there. Peak bandwidth is 7.4 terabytes per second. If you look at, say, Nvidia's B200, that also has 192 gigs, but slightly higher bandwidth, around 8 terabytes per second.
So slightly less bandwidth than the direct competitor. Is that significant?
It might be a deliberate trade-off. Maybe slightly less bandwidth allows for better power efficiency, which could be really important for inference workloads that run constantly. It suggests they're optimizing for efficiency, not just raw peak numbers.
Interesting. And there's something else special on the chip, isn't there? The sparse core.
Ah, yes. The 4th-gen sparse core. It's a specialized accelerator on the chip, and it does two key things.
Okay, what's the first?
First, it accelerates ultra-large embeddings. That might sound obscure, but embeddings are absolutely fundamental to Google's core business search, ads, YouTube recommendations. They all rely heavily on massive embedding tables.
So that helps their own stuff run better. Makes sense. What's the second purpose?
The second purpose is more about large-scale training and efficiency. It offloads something called collectives.
Collectives. Okay, break that down for us. What's a collective? Like a group chat for chips.
Sort of. Think about getting thousands of processors to coordinate perfectly, like for an all-reduce operation where everyone needs to sum up their results and get the final answer. That communication, that coordination is incredibly bandwidth intensive. That's a collective operation.
Okay, like getting a huge orchestra to hit the same note at the exact same time.
That's a great analogy. Exactly. The signaling and coordination is the hard part. By offloading that tricky coordination work to the specialized sparse core,
You free up the main compute engines, the MXUs, to just crunch numbers.
precisely. It maximizes what they call goodput, the useful work getting done,
Yeah.
instead of wasting cycles just managing communication. It's smart systems thinking.
Okay, let's talk physical design. This thing must be huge and power hungry. You mentioned chiplets?
Right. Ironwood is reportedly their first design using multiple compute chiplets on a single package, probably using a very advanced process node, like 3 nanometer.
Why chiplets? Is that just cheaper?
It's mainly about manufacturing yield and economics, yeah. It's generally easier and cheaper to make several smaller, perfect chiplets than one giant, flawless chip. Better yield means better cost.
But putting all that together generates a lot of heat, I imagine?
Oh, absolutely. These things require serious liquid cooling. They're deployed in these robust, cooled pods. You can't just stick one in a standard server rack.
Any idea on the power draw per chip?
Based on the system details, the inferred power per chip seems to be around 285 watts, which is, pretty high. It's up there with the competition. Nvidia's GB200 is estimated around 1,200 watts.
Wait, 1085 watts. But I thought you said they were prioritizing efficiency for inference. That sounds like a contradiction.
It does seem like it at first glance, but efficiency is relative, right? They're claiming a 2x improvement in performance per watt compared to their previous generation, Trillium.
Okay, so for every watt they burn, they're getting twice the work done compared to before.
Exactly. They're pushing the performance ceiling way higher, but they're doing it more efficiently than they used to. It's still a power-hungry chip, but the efficiency gains are significant.
Got it. Now, you mentioned the SuperPod, that 9,216 chip behemoth. That's the real unit they're selling access to.
That's the fundamental unit of compute for them at this scale, yeah.
So what kind of numbers does a whole SuperPod put out?
It's pretty mind-bending. Aggregate compute is 42.5 exaflops of FP8 performance, and maybe even more impressively, 1.77 petabytes of total high-bandwidth memory across the whole pod.
A petabyte and 3/4 of HBM.
Wow, and here's the really interesting claim from Google systems engineers. They say this massive pool of memory is effectively shared and directly addressable.
Shared. Across over 9,000 chips. How does that even work?
That's the magic they're claiming. It means the pod can essentially work as a single unit. For developers trying to run these enormous frontier models, that could radically simplify things like model parallelism, which is a huge headache today.
Making thousands of chips feel like one giant brain. That's the goal.
That seems to be the core idea, yeah.
But making that happen needs some serious networking inside the pod, right?
Absolutely critical. They actually use 2 different network fabrics. There's the local one called ICI Interchip Interconnect that handles the dense chip-to-chip communication within smaller groups, running at about 9.6 terabits per second per chip, likely in some kind of 3D torus or hypercube layout.
Okay, so that's the local neighborhood network. What connects the whole SuperPod together?
That's where the real secret sauce seems to be. OCS, or optical circuit switching, think of it as the system-wide superhighway.
Optical circuit switching. What's special about that?
Well, first, performance. It's an all-optical path. Because it's circuit switched, they can establish direct, dedicated light paths between any 2 points in the system. This enables massive-scale RDMA remote direct memory access, bypassing host CPUs entirely with near-zero added latency. It's incredibly fast for moving large chunks of data.
Okay, so it's fast, but you said secret sauce. Is there more?
The really profound implication, I think, is resilience. OTS isn't static. It can be dynamically reconfigured. So you can tailor the network topology perfectly to the communication pattern of a specific AI model.
The network, okay.
But here's the kicker. Because it's reconfigurable, OCS provides what they call ICI resiliency. If a link fails somewhere in the local ICI fabric, or even if a whole node goes down.
The OCS can just reroute the traffic instantly.
That's the claim. Instantly route around any hardware interruption. Think about what that means for training jobs that run for weeks or even months and cost millions of dollars.
A single hardware failure wouldn't crash the entire multi-million-dollar run.
Exactly. That's potentially huge. Google is touting fleet-wide uptime of 99.999%. 5 nines. For a giant enterprise customer running frontier model training, that kind of reliability guarantee, honestly, it might be more valuable than a few extra peak FLOPS.
Reliability is the killer feature, not just speed. Interesting.
It really shifts the value proposition, doesn't it?
Okay, this hardware is impressive, but hardware is only half the story in AI. We have to talk software. Nvidia's biggest advantage, many say, isn't just the GPU, it's CUDA, that 15-year-old software ecosystem.
Absolutely. CUDA is the moat. It creates a powerful lock-in effect for developers. It's familiar, it's robust, tons of libraries support it. It's a massive hurdle for any competitor.
So how is Google trying to counter that? What's their software strategy with Ironwood?
It seems to be built around their own compiler, XLA Accelerated Linear Algebra, and it looks like a two-pronged approach.
Okay, prong one.
Prong one is for the, let's call them performance elites, the folks already deep in Google's ecosystem, probably using JAX. For them, they've introduced something called Pallas.
Pallas, a new language.
It's described as a JAX native kernel programming language. It lets sophisticated users write their own highly optimized custom compute kernels directly for the TPU hardware, bypassing some higher-level abstractions.
So maximum control for experts. But doesn't writing custom kernels break things like automatic differentiation? Which is why people love JAX.
Ah, that's the clever part, apparently.
Yeah.
Pallas kernels are designed to be composable within JAX. Crucially, JAX's grad function, the automatic differentiation engine, can still see through the Pallas kernel. So you get customization and you keep the core JAX tooling.
Smart. Okay, so that's for the JAX experts. What about everyone else? The mainstream AI researchers and developers.
That's prong two, and it's arguably the more strategic move. They're fully embracing PyTorch.
Embracing PyTorch, that feels like a big concession. PyTorch is dominant, especially in research.
It is a concession, but a necessary one if they want broad adoption. They know they need to meet developers where they are, and most developers are using PyTorch on Nvidia GPUs today. They have to make switching to TPUs as painless as possible.
How are they making it painless? Because using PyTorch on older TPUs wasn't always smooth, right? There was that lazy execution issue.
Exactly. That was a major frustration. PyTorch code wouldn't execute immediately. It would get compiled behind the scenes, which made debugging and interactive development really painful. They've apparently fixed that.
Oh.
They're introducing full eager mode. Operations execute immediately, just like developers expect on a CPU or GPU. That should restore the rapid prototyping and research workflows people love in PyTorch.
That's a big deal for usability. Anything else on the PyTorch front?
Yeah, they're also integrating XLA tightly with torch.compile, which is PyTorch's standard way to get just-in-time compilation speedups. XLA becomes the backend for torch.compile on TPUs.
So the goal is make it feel completely native, like you're just writing standard PyTorch code and it runs fast on Ironwood without you having to think much about XLA or TPUs versus CUDA or GPUs.
That seems to be exactly the strategy. Abstract away the underlying hardware and compiler differences. Make the performance accessible within the framework developers already use. If they pull it off, it could seriously undermine the CUDA lock-in. Why pay the Nvidia tax if PyTorch runs just as well, or maybe even better, on a Google SuperPod?
Speaking of taxes, that brings us neatly to the other chip they announced, Axion, the ARM-based CPU. Where does that fit in?
Axion is playing a different but related game. It's more about the surrounding infrastructure, the stuff that supports the big AI jobs.
Like what kind of stuff?
Think data preparation, databases, web serving, running all the microservices that feed data to the AI models or serve the results. These are often huge workloads in themselves, and they typically run on general-purpose CPUs.
Which, until now, were mostly by 86 CPUs from Intel or AMD that Google had to buy.
Exactly. And those chips aren't cheap, especially at the scale Google operates. Buying them represents a significant cost, eroding Google Cloud's profit margins. People sometimes call this the buy 86 tax.
So Axion is Google's way of avoiding that tax.
Right.
By building their own custom ARM CPU.
Precisely. It's a margin defense strategy. Replace expensive third-party x86 silicon with their own custom ARM silicon, likely built on that same advanced 3-nanometer node as Ironwood. They control the design, the cost, the integration.
And do they claim performance benefits for customers too, or is it just about Google's margins?
No, they're claiming significant customer benefits as well. Better price performance. They're saying Axion VMs offer up to 2x better price performance overall and up to 65% better price performance, specifically compared to comparable x86 VMs.
So cheaper compute for those bread and butter cloud tasks.
Right. It makes the entire Google Cloud ecosystem, including the AI hypercomputer, potentially cheaper to deploy and operate because the surrounding CPU workloads cost less. It's about optimizing the whole stack economically.
Okay, let's step back. Big picture. Ironwood achieves something like per-chip performance parity with Nvidia's best, backed by this massive, resilient superpod system, and Axion tackles the CPU costs. Is this finally the Nvidia killer people keep talking about?
Nvidia killer is probably too strong, at least in the short term. Nvidia's ecosystem and market lead are huge, but Ironwood is arguably the most credible alternative we've seen so far, especially when you consider the whole integrated system.
So not a killer, but a serious challenger.
Definitely a serious challenger, but I think the longer-term threat to Nvidia isn't just Google acting alone. It's the collective action of all the major hyperscalers, Google, Amazon with Trainium and Inferentia, Microsoft with Maya. They're all building their own custom silicon.
To avoid the Nvidia tax.
Primarily, yes. They want to control their own destiny and reduce their dependency on Nvidia's high margins, especially for flagship GPUs. That collective pressure over time is what could really erode Nvidia's pricing power and market share.
While the giants battle it out, is there anyone else who wins from this?
Oh, absolutely. There's a sort of hidden winner here, Broadcom.
Broadcom, how do they fit in?
They are Google's key custom ASIC partner. They help design and manufacture the TPUs, including Ironwood. This whole custom silicon trend is massive business for them. Just the Google TPU program alone is projected to bring Broadcom over $10 billion in revenue in 2025.
$10 billion. Wow. So Broadcom is the picks and shovels play in this AI gold rush.
Exactly. They provide the essential tools and services that enable hyperscalers like Google to build their own custom chips.
Did the market see this Google announcement as a serious threat to Nvidia? How did the stocks react?
They definitely took notice. When the details really started circulating in early November 2025, Nvidia's stock actually took a hit, dropped about 3.6% the next day. That suggests investors saw Google's claims, especially around parity and the integrated system, as a genuine competitive challenge.
Okay, but no strategy is perfect.
Yeah.
What are the potential weaknesses or limitations in Google's approach here?
There are two pretty significant ones, I think. The first is the classic walled garden problem.
Meaning Ironwood and Axion are only available on Google Cloud.
Exactly. You can only rent them. You can't buy the chips. If you're a company committed to AWS, Azure, or you need a hybrid or multi-cloud setup, this Google hardware is simply off limits. That definitely limits the total addressable market.
Right. What's the second limitation?
It's the inherent risk of specialization. TPUs, being ASICs, application-specific integrated circuits, are incredibly efficient for the tasks they were designed for right now. That's largely transformer models and related algorithms.
But what if the next big AI breakthrough uses a completely different kind of algorithm?
That's the risk. An ASIC can become overfit to yesterday's algorithms. A more general-purpose architecture, like a GPU, might be less efficient today, but potentially more flexible and adaptable if a radical new model architecture emerges from the research community.
So efficiency today versus flexibility for tomorrow, that's the trade-off.
It's the fundamental ASIC versus GPU trade-off, yeah. Google is clearly betting that the current architectural trends will continue long enough for their efficiency advantage to win out.
So wrapping this up, what's the key takeaway for someone trying to make sense of all this?
Yeah.
It's not just about comparing chip specs, is it?
No, definitely not. The real battle here is ecosystem versus ecosystem. Google's advantage isn't just Ironwood's FLPS or Axion's efficiency. It's the entire vertically integrated co-designed stack.
From the compiler like XLA and the PyTorch integration,
Down through the custom silicon, the chiplets, the sparse core, the advanced packaging.
all the way to the optical switching fabric, the OCS, that ties the whole 9,000-chip superpod together.
Right. That complete system integration is their unique selling proposition. Ironwood and Axion are really the physical result of years, maybe decades, of internal Google R&D that they used for search and ads. Now, they've productized that internal advantage and are renting it out to the world via Google Cloud.
They're betting that integrated system can win the next era of computing.
It seems to be the bet.
Which leaves us with a final thought for you to mull over. We talked about the massive cost of training these frontier AI models, potentially tens or hundreds of millions of dollars for a single run. And Google is promising extreme reliability with that OCS interconnect 99.999% uptime, instantly routing around failures. So here's the question. For those huge, expensive training jobs, is that resilience, that guarantee your job won't crash, actually more valuable than squeezing out the absolute last drop of peak performance, the raw FLOPS? In this age of potentially billion-dollar AI models, is reliability the new speed?
That's a fascinating question to consider as these AI factories get bigger and bigger. What's the real bottleneck compute speed or the risk of failure?
Fun to think about. We'll leave it there for this deep dive.
Thanks for tuning in.
We'll catch you on the next one.